Hi everyone, can you hear me? That's good. All right, cool. So today we're going to present our paper that we've submitted to HotPets, but also to PIMLI, Privacy, Machine Learning, and AI, which is a workshop that's going to be co-located with ICML, International Conference on Machine Learning, something like that, yeah. Okay, so, and the basic proposition of the paper is to say that maybe we need to start working on HOTS, and we're inspired by PETs, which is privacy enhancing technologies, but we think that the character of information systems have changed, and in order to respond to these changes, we should move from PETs to POTS. To talk about what has changed in the information system world around us, is that we look at three specific shifts. I mean, this is a two-page paper. There's a longer paper if you're interested in this, that happened since the 90s in software engineering. There are three major shifts. One is the shift from shrink-wrap software to services. For those of you who are younger and who have never held a shrink-wrap software in your hands, in the 90s we used to go to places like Fnac, and there was a box in which the software was found, and it was shrink-wrapped. So that's where the shrink-wrap software comes from, which meant that the software would be produced, it would be put into a box, you would buy the box, you would take out diskettes, CD-ROMs, depending on how old you are, and then install the software on your device. However, with the 90s, with the rise of the internet and web services, software engineering moved from shrink-wrap to services, meaning that the code remained now in the hands of the developers, and services could be used using browsers or, by now, applications or apps. This also completely changed the way software is engineered, whereas before you might have a complete cycle of production where you come with the requirements and then design a system, implement, and then you finish and then you launch, right? You have a release where the whole process may take 2 or 3 years. Now software can be broken down into features which are produced as maybe minimum viable products, meaning you put one minimum feature out there to see how users react to it, and then you can refine it and experiment on it to see how you will actually develop the service further. So this has been, the move to services has been very important for the move that we see in software engineering from waterfall methods to agile methods. And if you can imagine that there are services and they can get direct feedback from the users and from the environment, or you're integrating multiple services, meaning you want to check to see if all the services that you integrated are still doing what they're supposed to be doing, and there's a lot of feedback, you have a lot of data. And if you have a lot of data, you need to put it somewhere, and we argue that we have also seen the shift from PCs to clouds, so instead of software being on your device, not collecting a lot of data, and you maintaining yourself, now we have services which collect a lot of data on the clouds. Okay, so this is kind of descriptive, but what we argue in the paper is that this has completely changed the character of information systems. And in fact, we think there's a shift from information communication systems to optimization systems. What do we mean by that? Whereas information communication systems, as the name suggests, is very much about collecting, processing, organizing, and communicating information. Now that we have this real-time feedback on everything that we do in terms of software engineering and creation of systems, we can optimize. So we can optimize the features that we're going to show the users. We can optimize actually how the users are interacting with our systems. We can start metricizing how user churn is going to happen, and based on that, completely change the way we organize the information system. So basically, there's a shift from being a vessel for collecting, communicating, and organizing information to being a device that doesn't really care about knowing, but that can do optimization. Okay? This means that there's also a shift in the problems that can be associated with these systems. When we think about privacy, we're worried that these are information and knowledge systems. They know something about you, therefore they can enact surveillance, and that surveillance may have bad impact on individual privacy or generally on society. However, what is different in optimization systems is that no longer is a concern predominantly with surveillance, but it basically is about systems that seek maximum extraction of economic value through the capture and manipulation of people's activities and environments. Right? You can constantly give feedback to users about how they're using the system to manipulate them into using the system in a certain way by the way you design the system or by the way you notify them. In fact, there's not much new about this. Some people have predicted that we would move into such systems. Here's a really beautiful paper from 2003, David Phillips and Michael Curry. They talked about the changes in location-based services. To do that, they talk about the history of geodemographic systems. Geodemographic systems are the ones that marketing and PR companies will use, or advertising companies will use, to know who lives in what neighborhood and what you can know about them so that you know what to sell them, right? So the idea of geodemographic systems when they came out in the 60s and 70s was where you are says something about who you are, right? And this is still the case. I was just talking with a colleague last night who looks at like life insurance companies in the Netherlands that basically calculate your premium based on your zip code, because your zip code says all about your income, right? It's quite an accurate identifier. However, with the introduction of GPS and location data, the geodemographic system providers understood that not only can we say something by looking at the location of somebody, so we can tell zip code, income, or we can look at a hospital or an AIDS clinic and say something about your diseases, but in fact we can co-create space. What do we mean by that? So if you think that I can now follow who is coming to Leuven at 9 a.m., I can say something about them differently than somebody who's coming here at 6 a.m., might be doing cleaning or maintenance. And basically, Leuven becomes something else with each and every one of these interactions. So space is co-created. So this means that the new location services not only see location and can infer things about individuals, but by virtue of seeing how people come together to create a space and being able to manipulate people to create a space, they can actually create ideal geographies from which they can extract profit. Okay, this is a little bit abstract. Do I need to explain more? Do I need to explain more? Is it clear? Okay. So Phillips and Curry suggest that by virtue of this move, companies can start to optimize space and start experimenting on space, so giving different information to different users, to create different kinds of ideal geographies, and to optimize in order to extract value and maximize profits. Now, what is the problem? We have seen a lot of news reports about some of these problems that arise from optimization systems, now that you can affect how people move and interact, and then optimize over those interactions. Some of the most typical one that was discussed already in the 90s is social sorting. So you can basically look at the population and find out which ones of them are very profitable for you and optimize over their interactions and over their needs. The Cambridge Analytica case is an example of mass manipulation where the optimization of the newsfeed, in the case of Facebook, was used to mass manipulate opinions. Then there's also the question of systems being very much, optimized systems very much adhering to the needs of the majority, therefore allowing for majorities to dominate in platforms or their needs to be responded to while erasing the needs and concerns and experiences of minorities. What's also interesting about optimization systems, by virtue of being very data hungry and being able to process data being a very costly thing in and of itself, and also being the first one to dominate a market, giving you amazing amounts of advantage, it does also lead to asymmetrical concentration of resources, which we find is evident from some of the larger companies that are basically major actors in this field. Now, all of this are still kind of socially recognizable effects, but we wanted to understand what is it about optimization systems that lead to these effects. So how are the objective functions defined, and maybe badly defined, lead to some of these harms?
Thanks, Seda. So I'll take over now. In the vocabulary of optimization, these harms that Seda has been talking about arise due to choosing inadequate objective functions that, among other things, create antisocial and negative environmental outcomes, have adverse side effects, only benefit a few, either users or non-users, externalize risks, produce errors due to some distributional shift, fulfill functions but not as its goal intended, or distribute errors unfairly. I'm going to cherry pick a few of these to talk about, the ones in bold here. So the first is antisocial and negative environmental outcomes. And for each of these, I'm going to go through a specific example that we've actually seen in the wild of this kind of behavior happening. So the first is this article on the perfect selflessness of mapping apps. And so in this article, the basic idea that researchers found was that if everyone is using maps at the same time, and some incident occurs on a highway, and the mapping app, they use Waze here, directs you away from the accident site, then overall the residual delay of everyone in the network in general is going to be much worse than if everyone had just done what what the roads were designed to do and had waited for the accident to clear. And the overall impact for everyone involved in the network is much worse. Even if for the small amount of users, it can potentially be better in the very short term. The next one we'll talk about is these optimization systems that have adverse side effects or only benefit a few of their users. In this one case in LA, they had a mapping app, again Waze, directing people down a super steep or up a super steep road in LA that wasn't meant for through traffic. And so people, the mapping app chooses this route because it actually is a shorter distance and in general quicker. But it's not one that's meant for lots of people to drive on, so it's very dangerous when you have heavy traffic there or people that aren't used to driving on this type of road. And you had lots of accidents, cars driving into people's gardens as they come around the corner, and this type of thing, where had you had normal city planning, no one would be driving on this road. The other nice example with Waze is that we have some of these nicer, quiet neighborhoods that are just off of freeways that have lots of children playing or are from kind of smaller towns that don't necessarily have the resources. And you have people going through these small towns instead of on the highway in ways that they never have before. And now these small towns that don't have the resources have to allocate their resources to these formerly neighborhood roads. In addition, they have to increase police presence on these roads, and kids playing can cause some issues there as well with heavy traffic. The last one we'll talk about is optimization systems that are sensitive to a distributional shift, or in machine learning we call this domain adaptation, or the lack thereof in this case. So Pokemon Go is this game with Pokemon, and it was originally the locations of resources in Pokemon Go were pulled from an old data set that was built by players of a game called Ingress, which the company Niantic owned as well. And this game was predominantly played by middle-class white men, and so the neighborhoods with the most locations in Pokemon Go now are going to be the same as they were in Ingress, which is these middle-class white neighborhoods, college campuses, this type of thing. And so the people who are playing in black neighborhoods in a lot of cities are seeing that they don't have any locations to play the game in, and it drives them off of the app, which essentially is an optimization problem producing redlining in the same way that it did traditionally. All right, so now that we've kind of talked about why there are problems, we're going to introduce kind of some of the solutions to these problems as they exist now in the wild. So I talked earlier about one of the problems with Waze, which is that it directs people through quiet neighborhoods that used to be safe from heavy traffic. And so one way that towns are reacting to this, or the citizens of the people in these neighborhoods are reacting to this, is by reporting false road closures or reporting heavy traffic on their roads in order to discourage users and also discourage Waze and Google Maps from sending users through their neighborhood. This is only moderately effective we've seen, but it's one example of this. The next, one of the problems with Pokemon Go, besides Pokestops and things not appearing in black neighborhoods, is that also people who are playing in rural areas have very few locations to get resources, but also very few Pokemon to catch. And so there are a few solutions that people playing in rural areas have done to fix this. The first is just by spoofing their location to somewhere that's more populated where they're going to catch more nice things. Kind of the more creative pots, if you will, here are Pokemon Go uses Open Maps as its mapping application. And in its algorithm, it puts more Pokemon on footpaths and parks and places that there are water, like for say a swimming pool. And so Pokemon Go players were editing Open Maps, because you can do that, to include their backyard as a park or a pathway that goes through their park, or saying they have a pool or a pond in their backyard, and all of a sudden saying, excellent, I can play now in my backyard, I have lots of Pokemon. The third one we'll look at is Uber. So Uber drivers are notoriously underpaid. In most jurisdictions, they're making less than minimum wage. And one way that they've reacted to this is by creating an artificial surge. That is, they collectively get together online and say, at this time of day, we're all going to shut off our Uber apps. So they all shut their Uber apps off, and then a few minutes later, they coordinate again, everyone turning their app on at the same time. And in the meantime, while their apps were off, the Uber algorithm sees, we have lots of people who want rides, even though that number hasn't changed. But we don't have very many Uber drivers to pick them up, surge. And so now every person who gets in an Uber for the next 10 minutes pays the double or triple or quadruple price for the Uber surge that they've created artificially. And every Uber driver who participated in this, plus the peripheral ones that just happen to be in the right place at the right time, get a jump in their income for the next ride that they have. And now I'll pass it on to Ero to formally introduce what is a pot.
So the problem with the responses that Rebekah has explained is that they're actually a rather ad hoc. And while they demonstrate the creativity and the determination of those that are put at disadvantage by the optimization system, they are not necessarily very effective, as users have in general a limited understanding of how these systems work, and often lack the resources and skills to go beyond these rudimentary solutions. So our question is whether we, as computer scientists and engineers who have the technical skills to understand, analyze, and design these systems, can actually design tools that address the needs of these users and non-users, and hopefully provide a more solid and coherent response to optimization. And we call these hypothetical tools bots, which is the short for protective optimization technologies. So bots are, in essence, the deployment of adversarial learning. This is exploiting the design and rules of a system to turn it to our advantage through carefully modified inputs. The acronym is suspiciously close to PETS for a reason, which is that privacy engineers have been doing this for years. This is examining a system that is privacy invasive and design privacy-enhancing technologies that users can rely on to address an externality, in this case privacy loss, while still reaping as many of the benefits they expected from the original privacy-invasive system. So how can we model this? How can we model bots? We will first start with the optimization system without the bot. So we can conceptualize the optimization system as a black box that takes a set of inputs from users that we denote as U, and a set of constraints from the environment, which we denote as E. So for instance, in Waze, in the case of Waze, or any other location service, this will be information from the needs of the drivers, but also information about the status of the roads and the maps and so on. So the optimization system with these inputs is going to actually, so we feed these inputs to the optimization system that will generate a set of responses according to an optimization function f. For instance, in the case of Waze, this could be like the shortest or the quickest route between two geographical points to drive. Now, the important part is that the outputs O will have an impact in subsequent inputs. So if Waze starts sending more drivers through a route than the capacity of the roads cannot cope with, the road will become congested, and this will change the constraints and the environment E. Some drivers may also join in the process, some other drivers might stop driving, and this means that actually the system will have to respond to these dynamic changes. So you see that actually these changes will actually depend on the inputs and the output, and it will be this closed loop, this feedback loop. So the optimization function will always be generated outputs that will determine the inputs and so on and so on. So how do we plug bots into the system? Well, the first thing that we need to do is that the bot must actually understand how the system works. And we can do this by, for instance, if there is information about the implementation of the system itself, we can do this analytically, and we can try to model the system mathematically. But more often than not, what we will have to do is to actually plug the bot in vivo into the system. So actually examine the outputs, change the inputs, and see how the outputs actually change and respond to actually changes in the inputs. So having an idea, so once we actually understand how the system works, the pod can start tweaking inputs and constraints to change the responses of the system, which again will feed back into the system, prompting further responses and adaptation from the optimization system, and that will prompt, in turn, more optimizations that we will have to do at the pod. So, an important thing to note here, to consider, is that we no longer consider just the set of original users that the optimization system considered, but also like other people, like non-users, people that are actually affected by the system. And we not only consider the constraints that the original optimization considers, but also other features that that system might have not accounted for, and also like an extended environment. So for instance, like points in the geography that we're not actually taking into account. And this could be, for instance, like in an environment, the fact that there is a school or there is a home for the elderly, and so on and so on. So now that we have a model, the question is, how could we design a pod? So what should a pod do? So first we need to define what is important to us. So do we actually need to increase road safety? Do we need to, would we like to actually have like a minimum number of Pokemons in certain areas and ensure there are enough Pokemons in rural areas? Do we want to actually make sure that the drivers of Uber can get the minimum wage? And this we will do through what we call a benefit function view. With this, we can actually evaluate how the system without the pod works. So for instance, in this case, we look at the outputs of the system, we run them through our benefit function, and see that this creates a set of like local minima for particular users or non-users in the system. And this we are not actually happy with, and we would like to correct. So there are actually many things that we can do from now on. So we can actually try to start tweaking the inputs to the system in order to correct these imbalances, let's call them. So for instance, we could correct imbalances in two main ways. One of them would be to actually redistribute the benefits such that everyone is closer to the average. And this is actually represented by the green line. But also in systems where there is no scarcity of resources, such as is the case of Pokemon, we could actually want that we want to lift everyone's benefit as much as possible. So everyone is up on the blue line. Or we might actually want to use a pod to try to reverse the conditions for those who bear the burden and those who benefit as a form of protest. Or disagree with the system entirely and wish to destroy it, in which case we might want to sabotage the operation of the system by inducing random, inconsistent outputs. And that would be first, so that the reverse would be the red line, and the sabotage would be the pink random outputs. There's practically an endless list of possibilities of things that we can do, tweaking the inputs to the optimization system. Now, an important question that we have to ask is, should we do it? So we can do it, but should we do it? Is it ethical to bias optimization at our advantage? We're manipulating inputs, feeding misinformation to the system. Isn't this wrong? This is in essence what obfuscation systems do, which Brandon and Nisenberg have been studying for years. Although the goals of pods and obfuscation are not entirely the same, and I mean they're actually quite different, Brandon and Nisenberg have considered several challenges in their study of the ethics of obfuscation that we actually kind of like review and reapply to the case of pods. So the first issue that we consider is, so what is the input of dishonesty and polluted databases? Is it justified to feed misinformation to the system? Well, we might argue that since the end goal of optimization systems is not about objectivity or knowledge, as Seda was saying earlier, but about optimizing resources for a particular end, we're simply providing additional or better information for these systems to recognize the externalities that they fail to account for. Second, as for wasted resources, it is true that in certain cases the pods will actually increase the cost that the service provider will have to actually bear. But we could argue that this is actually about pushing back the burden of optimization back to the entity, which is responsible for the burden in the first place. Third, we could also say, well, if a few users actually deploy these pods, they will benefit at the expense of other users. So aren't these free riders that are actually kind of like optimizing their outcomes at the expense of everyone else? If we think about it, this problem is actually inherent to optimization systems on their own, as they often disregard non-users. Thereby, users are typically, by default, free riding on non-users. And in fact, if we really think about it, like if we really think about the using pods and the problem of re-optimization and counter-optimization, we realize that pods engender and replicate the same problems that they are trying to solve, which is the problems that optimization systems generate. And who are we to decide what the outcome of the system should be? Whichever counter-optimization strategy we choose, whichever they be, they might be users who do not agree with us, or we might actually negatively impact by our choice of B. Also, shouldn't we simply try to make optimization systems better by default, instead of trying to hack or improve the system a posteriori? And the answer is yes, absolutely. But again, we have to consider that it is impossible to account for all the constraints or make everyone happy. So we need tools to actually give disempowered users and non-users a mechanism to respond to harmful optimization. Moreover, pods will be made anyways by adversaries to try to gain the system at their own advantage. So we might as well try to devise alternative pods for the greater public. And this concludes our presentation.
Cool.